Log on, tune in, find out. Another good idea from Cambridge.
Any questions? The slides are going to be available, they told me, on the web, but you want to see them before they're available, you can send me an email. I will be happy to send them to you. Okay, so let me recap what we talked at the end of last lecture. An interesting problem is to do photoacoustics for the case of the brain. And one of the problems is here you have a discontinuous sound speed. Okay, so C is not any longer smooth. And so what you do is use the PDE is to solve across the discontinuities here a transmission problem. So transmission problem means the normal derivatives match and the solutions match. And you solve the wave equation in each part. Okay, and a different issue than the case of smooth sound speed is that the singularities, if you start with a singularity here, it will maybe never get out. So you have what's called total internal reflection, so that you have natural trap geodesics. At a certain angle, you calculate the angle, in fact, in terms of the index of refraction of the two mediums. There are some rays that never get out. Okay, so we have in some sense to neglect those. But for the ones who get out, there are still difficulties because some rays reflect and some rays refract, and then you lose energy in every step. So when you measure at the boundary, you may have much less energy than the initial one, but still you want to recover what the initial source was. Right? And so that means for the case of smooth sound speed, you essentially need just to take the first term in the series, in the Neumann series. So the main results, okay, here by the way, is again you assume that the initial data is supporting a compact set, and we are assuming that all the rays starting on this compact set, all the geodesics leave eventually to the boundary. They may reflect or refract many times, but they eventually leave. And so we consider this projection from the energy space, this is H1 0, to the case of to the compact case, in order to just consider functions supported here where we know the rays will get out eventually. So that's the main difference. And so the theorem is that you have the same. You have again to project, because we need to have the function supported on that compact set. Is the identity minus k, and still k has norm 1 for t sufficiently large. And so you can invert using the Neumann series. But as I said before, in order to recover the f, a lot of the times you have to take further terms in the Neumann series. It really depends how many reflections you have. From getting from here outside is how many terms you have to take. Every consecutive term in the Neumann series means you have more reflections. But still you can, and you can do it, and you can get very good pictures, as I showed you before. There is one ingredient that was not known before for the case of discontinuous sound speed. The propagation singularity was not well known. Is the Tatarus unique continuation theorem, but an extension of, we prove an extension of that for the case of discontinuous sound speed, and it's exactly the same result. Okay. So again, here is the pictures, the velocity, the Neumann series with 2 times the diameter, 4 times the diameter, 8 times the diameter. Of course, it gets better. Time reversal, as I said before, creates spurious rays when you propagate back. So that's why the pictures are not are worsened in the case of a smooth sound speed. So this is original Neumann series time reversal. And you also can see you cannot recover well everything because there are rays that never get out. You have trapped rays inside. But there are a lot of the rays get out. That's the main problem. That's why you can get a picture. Okay, so the final topic for that part of the wave equation is the case of measurements on part of the boundary. You have heard a lot about partial data for Calderon's problem. And for here you can do pretty complete analysis for the case of the wave equation. So you take an open subset of the boundary and you make measurements only on a subset. And again, we have F's supporting that fixed compact set. So what can you do there? What do you expect? So for uniqueness, you have finite speed of propagation. This is in the smooth case. For uniqueness, so you have here your domain. And here you have part of the boundary. Sorry. Yeah, so here is domain as part of the boundary. You have to be able to get a signal from any point. Okay, so if you take any point, the signal must get to the set gamma somehow, otherwise you cannot make the measurement. Right? So we set at a particular time here, depending on this compact set, the maximum distance from the points in the compact set where the support of the initial data is to the boundary. The distance again is in the metric related to the sound speed. And the uniqueness condition should be this. And it is. And we need some further condition. This is just a technical condition to be strictly convex. So this is you can choose pretty much the domain where you want to enclose to recover what is inside. Right? Then if T is sufficiently large, bigger than this number, then you have uniqueness. And again, we use Tataro's uniqueness result. For stability, so I should ask, before I show this, let me ask the question, what do you expect for stability? When will you have stability for this problem? What is the key in the case of sound speed, smooth sound speed, and even in the case of non-smooth sound speed, is how singularities propagate. Right? If the singularities here reach there, this is the set where you're making the measurements, you are going to have stability. So the geodesics have to reach this set, gamma. Right? That should be the condition. And the geodesic doesn't have to be the full geodesic. You may have the part going forward for positive time. This doesn't matter that it doesn't reach the boundary gamma where you're making the measurements. Okay, so this is so to be able to, so the heuristic argument is to recover F from lambda F in a stable way. Stable means, somebody asked me at the beginning of the lectures today, what does it mean stable in Sobolev norm? You have Sobolev estimates. We need to recover all the singularities. So we should require that for every point and a direction, the ray, the geodesic through it, this is where the support of the function is, reaches gamma at the time where you're measuring. So this is essentially if and only if condition. So the only is a small technical thing whether you include the endpoints or not. So the theorem is a stability condition is not satisfied in the closure, then there is no stability in any Sobolev norm. And this tau is the time that you need to reach the boundary from a point x plus or minus c. Okay. So the reformulation, so here you have a picture, this is gamma, much larger than there. So here is your point, x. Okay, so this ray, this part of the ray reaches gamma, so it's fine. And here this part of this ray reaches gamma. This part doesn't reach it, but that's okay. The singularity reaches gamma. So you have the same time. So you need this time, t bigger or equal than t1 over 2. Remember, t1 was the length of the supremum of the length of geodesics. You need time bigger than t1 over 2, so that at least part of the geodesic intersects gamma to have uniqueness and stability. To have stability. How about reconstruction? Reconstruction, we don't have the same method for reconstruction of a Neumann series. Does not work. At least we couldn't make it work. So what can you do? So this is very similar to the reconstruction method that you saw in Adrian's talk. Instead of inverting a Neumann series, what you can derive a Fredholm equation for the data that you want to, for the function that you want to recover in terms of the data. And you show that the Fredholm equation is uniquely solvable. Okay, so it's not as explicit as in the case of when you have full data, but it's still you have some reconstruction, and we have tried numerically. So I'm not going to, this is for the people who know these words, this is some microlocal analysis. This operator A is, what happened? Is a time reversal operator. This is, what is happening to the, okay. Seems I'm disturbing the image when I do this. Oh. I don't have power. Okay, so this is for the people who know these words. This is uses more complicated macrolocal analysis. This is a zeroth order classical pseudo differential operator in the neighborhood of the place where you have your function has support, and it's elliptic. And it's a Fredholm operator, and you have a stability. Okay. So you reduce the problem. This is what I mentioned before. In the case of partial data, this is technically more complicated. I'm not going to go through the details. I just want to tell you. You have a Fredholm equation of this type in terms of the data. Lambda f is the data, chi is a cutoff, where you have partial data here. B is a parametrics. It's an inverse. And this is a compact operator, modulo smoothing, modulo compact operator. And actually you show that this is an elliptic pseudo-differential operator that you can invert with the symbol strictly less than 1. So you can solve for f in terms of the data. Of course, but to invert the Fredholm equation numerically is much harder than to invert it using Neumann series, but you can still apply the formal Neumann series argument and sum this in, for the people who know this, in the Borel sets to get back the f. And this is what we did to get pictures. So again, I repeat, the Neumann series does not work in exactly the same way, but you can write down a Fredholm equation for the f in terms of the data. using some microlocal analysis. I cannot go through it. And you get these pictures. This is the original, and here you're missing one side, this side, and here you're missing two sides. Of course, you don't expect the pictures to get closer to the sides that you're missing to be as good. Okay, so now let's go to the second step. So let me finish by considering the second step. Remember from before, so let me, and this is from the first lecture. So this was just the first step. This is not what we're trying to do originally. This is a step towards solving the problem. So we send a laser beam or some electromagnetic wave, and this is absorbed, and you have a thermal expansion, and that produces acoustic waves, and then you try to get the image formation. So the part that we have done so far is to solve the case of the wave equation. So we solve the inverse boundary problem for the wave equation. That's when you measure here. And we have found the initial data of the initial source, the thermal absorption inside. So this is a function which is defined everywhere inside the domain. And now what you want to do is to find the optical or electrical properties of the domain. That's the second step. And this is an elliptic problem. So in quantitative photoacoustic tomography, in the diffusive regime, so the optical radiation is modeled in the following way. This is what's also used in optical tomography. Gamma is the diffusion coefficient, and this is the absorption or the conductivity. And you have this elliptic equation, and U is G on the boundary. So the boundary has been changed in notation from omega to X. And you can see that different slides, written in different times. Okay, so this is an elliptic problem, and what you are measuring, what you already have from the first step, is this h of x. So it depends on sigma that you're trying to recover and some other coefficient gamma, capital gamma. Okay, so there are three coefficients here: gamma, sigma, and capital gamma. Usually this one is assumed to be constant and known, but there are some cases where that's not the case, and there are some results about that. So we want to recover these three coefficients in principle from the knowledge of this. This is what we have already obtained by solving the wave equation. And we put some illuminations on the boundary. So we had to find good illuminations on the boundary so that the internal measurements that you are making, now this is known in the whole open set, not just in the boundary, like in the case of Calderon's problem. And then what we want to determine is how stable the reconstruction is. If it's not stable, then why are we doing this? We can just go back to the Calderon problem, which is unstable, and how to choose the illumination, how to choose this boundary data. And this is very much related to what you have heard in the previous lecture. What we are going to do is use complex geometrical optic solutions. I think you didn't call them that way, I guess, did you? But that's what I'm going to remind you of this in a moment. And for thermoacoustic tomography, what you send is lower frequency waves, because in that case you can expect deeper penetration, and the model is different. This is the model, and the internal measurements, this is what we know, and the internal measurements are given by modulo of U squared, where U is the solution of this equation, and this is the illumination. So this is the internal functional that you're trying from which you are trying to recover sigma. Okay, so this is quantitative thermoacoustics tomography. So for the first case, so what will you do for this? This is a test not for my course but for Adrian's course. This is very similar to the conductivity equation, except that we have an additional term here, but this is just lower order, doesn't play much of a role, at least for the theory. What will you do here to find solutions of the question? The problem is to find good solutions so that you can reconstruct the parameters, gamma, sigma, and even h if possible. So what will you do? You did that you saw that in the case of Calderon's problem. So suppose you don't have the sigma, you have that and data G on the boundary. What did you do? You reduce it to the Schrödinger equation, right? By making the transformation square root of gamma times mu, and that reduces to the potential to the Schrödinger equation, and this is the potential. Okay, so you will reduce this equation, and this of course will be a factor in the potential as well. And the theorem we proved with Guillaume Ball, we assumed that we knew capital gamma here from the coefficient before. We're just trying to recover two coefficients from two measurements. These are the measurements given by the wave equation, and we eliminate sigma, and we define this beta, this vector field. So this is the gradient of h2 over h1 times h1 squared. This is just some algebra that you do, and so we consider that vector field, and we had to find the integral curves of that vector field related to beta. So we are going to have G on the boundary, and we want to march in somehow. So to reach any point x, in order to be able to recover the coefficients. So we are going to reduce the equation to a vector field equation with the factor beta there, which is a gradient vector field. And so we need that the integral curves of this vector field reach every point x. So given a point x, you have to find an integral curve of this vector field related to beta. This is, I didn't show how to do that reduction, but it's just eliminating sigma from the equation. That comes out very easily. So we need that, for instance, this vector field be bounded from below. And we're dividing by h1, that this solution is non-zero. So you have to have no critical points. So the theorem is that the theorem that we proved that chi and q uniquely determine h1 and h2. So you can recover two coefficients. And Ball and Ren show that you cannot recover the three coefficients as expected with two measurements. Even if you add measurements, you still cannot recover the three coefficients. You need some transformation. For the case, so this is what is, so this is the reduction to the Schrödinger equation. And the condition that we need, and if conditions, is this vector field, as I mentioned before, this vector field beta be non-zero. I just want to more than explaining the details of this, I want to make a connection with the complex geometrical optics solution that you saw for Calderon's problem. So the problem is, so take this for granted, is to really construct solutions so that this vector field is non-zero. So in particular, you need no critical points for this solution. So assuming that you can find that vector field, this vector field satisfying this condition, we prove stability with the method of characteristic. We just integrate along the integral curves of the vector field. You start from the boundary, you integrate along this, and then you get a good stability estimate because we can penetrate inside. So this corresponds to 2 H's. H is what you measure. So in the CK norm, you have a stability estimate. Even in the cases discontinuous, Cui ran did some numerical calculations. When you have discontinuous parameters, then you still can get good reconstructions. But of course, we don't have the theory for that. And for the other case, when you have the electromagnetic wave is lower, of a lower frequency, this is the model. I'm giving out my, sorry, what is, sorry. So I have to finish, so when do I finish? Oh, no, I have 15 minutes. Okay, good. Okay, so how about quantitative thermoacoustic tomography? So the model there is different. So this is the model we're going to take, and we're trying to recover the conductivity sigma here. And again, these are the illuminations, and the functional that you're taking, all of this requires modeling, is sigma times modulo of u squared. So you lose the phase of the solution. And the theorem is, this is in inverse problems with Guillaume Bal, Cui Ren, and Ting Chodo is here. So if sigma and sigma tilde are uniformly bounded in HP, the Sobolev space for p bigger than n, then you can find illuminations so that you have uniqueness. Illumination, you can find boundary illumination so you have uniqueness. H is equal to H tilde implies that sigma is equal to sigma tilde. Remember, this one is the internal data that you're given, and you have good stability estimates. And the way to do it, maybe if I have time at the end, I will describe it in the blackboard. We apply Vanna's fixed point theorem to some appropriate function in the construction to prove this. I will maybe, since hopefully I will have a little bit of time, I will mention this. So how to, for the case of quantitative photoacoustic tomography, how to find this vector field which is non-zero? Okay. So for that, we use complex geometrical optic solutions like in Calderon's problem. I will erase this part. Oh, I don't want to erase that. So the problem is what you have a lot of choices. You can take any solution that you like and measure. In this case, you're measuring sigma of x times u times the solution. So what are the solutions that you're going to use? We need some kind of explicit solutions so we can compute this vector field. And the solution that we take for the Laplacian plus potential, you have reduced the conductivity equation to the case of Laplacian plus potential, are these solutions that you already saw. Okay. And with rho is a complex frequency, and rho is equal to 0. Okay, and what is the property that this satisfies? This is another test. Not for my class again, I'm doing the test for Adrian's class. What is the property of this? I get very little response. That the norm of this, and this can be done depending on the regularity of the potential. So here we needed a lot of regularity on the potential. For instance, if you want to have HP, it's less or equal than this times the norm of Q in H, if Q is in this Sobolev space. So this decays for large complex frequency. Okay. So these solutions, since it's written there, we call it CGO solutions. In analogy, this stands for complex geometrical optic solutions. Because they are analog of the real geometrical optic solutions, and here, as Adrian explained, you will have an oscillating phase and then lower order term. Why do you take this? Because if you take, for instance, the real part or the gradient of this part, which is the main part of the exponential, is just rho. And that's just a constant vector field. Of course, you're taking the real part, and it's non-zero. And so that's exactly the computation is done here. If you take u to be this, and then you do the computation that we need for the beta that was before. Right? So this is the imaginary part of the binary part of this. Is the binary part, I guess I'm taking. It's a constant vector field when rho 1 is k plus k1 k perpendicular, and rho 2 is equal to rho 1 conjugate. Okay. So the illuminations that we choose on the boundary can be CGO solutions or close to traces of CGO solutions. So this is another use of complex geometrical optic solutions in a different context. So we obtain nice vector fields, and the important thing about the vector field, as I mentioned before, is that this vector field be non-zero. And then we get stable reconstruction. So this complex geometrical optic solutions give you a possibility of constructing vector fields which have nice integral curves, and that's what you use. Okay, there may be other solutions, and in 2 dimensions, this is in any dimension, you have more choices of finding solutions, but in 3 dimensions or higher, these are the ones we know well. Okay, so there was a condition if that we have to use for both quantitative photoacoustic tomography and for quantitative thermoacoustic tomography. For quantitative photoacoustic tomography, we use the absence of critical points of a vector field, beta. In quantitative thermoacoustic tomography, we use a contraction argument in a Banach space that I will explain in a minute. So the existence of this set of illumination, which is an open set, so you take the CGO solutions and you show also that close to those work, because the vector field is still going to be nice, for instance, in the case of quantitative photoacoustic tomography, such as these properties hold, and those are these solutions that I just described. Okay, so let me come back to this here. So let me explain the Banach space type argument. So we are measuring sigma of x times u squared. Remember, that's a different measure in quantitative thermoacoustic tomography. And the equation for U is Laplacian plus k squared of U plus E sigma x times U is equal to 0. So this is the potential Q of x, right? So we're trying to recover sigma. So we want to recover sigma from this type of measurements. This corresponds to the H that we obtain by solutions of the wave equation. This is the amount of internal energy. Okay, so what do we take? U to be e to the x dot rho 1 plus psi q x of rho. This depends on sigma. Let me write the dependence. This depends on sigma, an explicit dependence on sigma. So modulo of U, so we take two of them. That corresponds to two different conductivities, sigma 1 and sigma 2. So sigma I here. Right? And so what are the measurements? The measurements are, for every I, is sigma of x times e to the rho plus rho conjugate dot x. Right? Is equal to what? So you will have two of them, right? Sigma times e. If you have two, you want to prove stability. That this is the I call it there sigma and sigma tilde. Here I'm calling them sigma 1 and sigma 2. Is equal to what? Sigma of x, right? Sigma of x times 1 plus psi sigma 1 plus psi sigma plus psi sigma conjugate plus psi sigma times psi sigma conjugate. Right? So it's sigma of x plus a nonlinear functional. I use k for something else, so let me use h. Well, h is, I use it there. G is not the Green's function again. G of sigma, right? So G of sigma is psi sigma plus psi conjugate sigma plus psi sigma sigma. Okay, so how do we solve this? This decay for large sigma, for large rho, right? For large complex frequency, this decay. So this is the identity plus a nonlinear operator. So what we show is that this is a contraction in the Sobolev space. It's P bigger than n, I believe. There it is written, contraction on Sobolev space where P is bigger than n for rho sufficiently large. So you can find a unique sigma solution of this equation, and moreover, if you take two of them, you can estimate. It's a simple estimate because you have that the norms of this decay for large rho. We can easily prove that the norm sigma 1 minus the norm of sigma 2 is less or equal constant times sigma 1 minus sigma 2 in the space Y. So for large rho, this can be made small, and that's the way you can prove this stability estimate. Okay, so in both cases, in quantitative thermoacoustic tomography and in quantitative thermoacoustic tomography, the use of complex geometrical optic solutions has been critical, although there might be other methods to do it. Okay, so somebody asked me this morning a question about trying to recover both coefficients, whether the sound, in all of these, the sound speed was assumed to be known. Where is the person? So can you recover both coefficients? That's a very interesting problem. Can I erase this? Cover C of x and f. So again, and this is coming to the wave equation. And you're making the measurement u at 0t across the boundary. Right? Well, it's not known, and that will be nice to know. We prove with Plamen Stefanov using Kahneman estimates that if you know for a single f that defines, if f is 0, there is nothing you can do. You cannot recover C, right? You need some conditions on f. If f is 0, the solution is 0, and so therefore there is nothing you can say about C. So we need some condition, and the condition that we need is that the Laplacian of f be non-zero. It's not a harmonic function. And that comes out naturally from the method of using Kahneman estimates to do this. Okay, so, but that's assuming that you know the f. So we prove that then in that case you can recover the C under some geometric conditions. So the question is it true that you can recover both? But f is the final, is what you want to do for photoacoustic tomography, and in a lot of cases they assume that the C is known. They have a model for the sound speed, but that's not always the case. And with Plamen Stefanov we have some initial calculations that show that the linearized problem, so this is a nonlinear problem now. Before, when C is known, this is just depends linearly on f. When this is present, this is nonlinear. If the problem when given f you want to recover C is also nonlinear, so it's more difficult, it's not solvable. So the conjecture is, unless there is a big surprise, huh? No, to reconstruct both. Oh, with one f, right, with one f. Yeah. If you have a lot of f's, then you can reconstruct the sound speed. If you have a lot of f's, you can reconstruct the travel time associated to that, for instance, and then you can recover the C, at least with some conditions. But this is just assuming one f. It's not solvable, but still that doesn't mean the nonlinear problem is not solvable, although one expects that it will not be solvable. Okay, so I decided to lecture on photoacoustic tomography and thermoacoustic tomography because I believe this hybrid type method have a lot of open problems for young people, and I just wanted to give you a very broad idea, at least in the case of photoacoustic and thermoacoustics, what are the methods and the problems. For instance, let me mention one problem. To suppose for the quantitative thermoacoustic tomography is you have this continuous sigma. What do you do in that case? We assume a lot of regularity because again we reduce it to the case of the potential. Another interesting problem is to consider the case of propagation of elastic waves. For instance, in the brain, it's more of elastic medium, and actually it's a viscoelastic medium. You have also some absorption. So further modeling on the wave equation is needed for the case of the brain. There are many, many open problems for young people like most of you. So this is a good subject. This is my main point. Okay, thank you.